Greetings and welcome to this video that is part of a series covering strength of materials and mechanics of materials. In this one we will be covering torsional stress. So if you have a member that is in twisting or in torsion, it creates a stress. This example is specifically with regard to power transmission. Uh, Transmission shafts, say, need to run from a generator to some kind of work that they need to do. Perhaps it's a pump, it could be an engine for some transportation method, it could be a variety of things. So we need to design and produce them properly and specify them properly. In order to transmit the power, they use torque from one end of a shaft to another. So I'll give you an example of what that might look like. Here is a shaft that we're going to be using, and it's 40 millimeters diameter here, 50 millimeters in diameter here. I have it designed as a solid shaft. And in order to move from one receptacle to another, perhaps, it is a smaller diameter here, a larger diameter here, and we have a certain area here where there's a step or a shoulder. And I have that as a 5 millimeter shoulder, which makes sense here. So it's a total of 300 millimeters long, 100 millimeters here, so that leaves this section as 200 millimeters. So the key governing equation here is power is equal to torque times the speed, which is basically how fast it's turning. Now, power and torque actually have the same units. The difference is that torque is simply a twisting. If it doesn't go through any turns, if you're just trying to twist something, say a nut on on an assembly that's just not moving, you're not actually putting any work into it. So if it actually goes through an angle at a specific rate, that's where this N comes in. So power is the work divided by time. This is the work and then through the angle divided by time here. This is power. This is torque. And this is angular speed. Now, in order to work with the units that we usually use, angular speed, whether you're using US units or SI units, angular speed is usually in revolutions per minute. Well, that doesn't necessarily work with our other units nicely, so we have to add in a factor here of 2 pi radians per revolution all over 60 seconds per minute. And that's, again, whether you're using US units or SI units. Rearranging this, if you need to find the torque, and we'll need to use this at some point, is P over N times 60 over 2 pi. And that's N is in RPMs. Now I've got some shortcut forms for you for US and SI units. So if you have specifically US units, we have power in horsepower is equal to torque in inch-pounds times N in RPMs. And horsepower is a funny thing, so in order to make this work with the RPMs, we simply divide it by 63,025. So you don't have to worry about what units this are or that are. As long as you put everything in here in these appropriate units, then you'll get out what you're looking for, whether it's horsepower, inch pounds, or RPMs. Then it's a good idea to translate. Maybe you need foot-pounds. Well, then retranslate this torque of inch-pounds into foot-pounds as a secondary step. Okay, for SI units, power is going to be in kilowatts because watts kind of small. Obviously with kilowatts, if you wanted to change it to watts, simply divide this by 1,000. And the torque is going to be in Newton meters times N in RPMs. And then for its conversion factor, it's 9549. Now you might get one book that says 63,000 and another one that says 9550. That's okay. The rounding in significant digits will not be affected by minor differences like that. Okay, so these are the shortcut forms for you. I could go into the derivations of these, but you can do that on your own if you want to, or go online and check that out. What's important to see in these equations is that power is dependent only on torque and speed. Notice that if you have a lower speed, you are going to produce less power. So faster speeds allow for more power transmission. Higher torques allow for more power transmission. Very simple linear relationship like that. Okay, now for our problem, we're going to use that shaft that I showed before. And I'm just going to paste a picture of it in here. There we go. And now remember, each of these dimensions is in millimeters. So next we want to list all the givens for this problem. So, all right, what is given for this problem? Again, you won't find this in a textbook, so just got to write them down here. We're going to use a common high-strength material, 6061-T6 aluminum alloy, and we want to transmit 7 kilowatts at 300 RPM. Okay, so we've got the geometry, we've got the material, and we've got the loading. So that's pretty much all we need for that. And what do we want to find? We want to find a number of things. Torque on the shaft. We want to find the stress at each end. We want to find the stress at the shoulder. And angle of twist. It's going to be a complex one. And finally, allowable power. Okay, this is what we want to put through, 7 kilowatts. Might want to know how much is too much. So we want to find what level of power would be unacceptable. Okay, and that is going to be based on, from one of our books that I like to use, we have n equals 12 based on ultimate strength. Okay, so we'll have to look that up. And what are we going to use? We are going to use our favorite power equation, and because we're using millimeters and we've got kilowatts here, totally makes sense to use our power in kilowatts equals torque in Newton meters times N in RPMs all over 9549. That's how we'll find the torque on the shaft, because we've got everything else here. And we need to find the stress at the end. So our torsional shear stress is equal to torque times C, which in this case is simply a radius, divided by J, the polar moment of inertia. To find the angle of twist, we're going to use theta equals torque times the length over JG. Now G is a material property. J is not, though. J is the polar moment of inertia, and that's not given, so we'll have to calculate that too. For a circular cross-section, it's pretty simple. It's pi d to the fourth over 64. Now, some things we have to look up now that we see what we're going to be using. We'll find the torque using this equation, stress using this equation for both of these. Here we've got angle of twist, and for allowable power, we'll go back to this equation. But we need to look up G, which is a material property, and also notice we've got that ultimate strength that we'll need to use. So going to look up a couple things. All right, what don't we know? We don't know G, and this is for the 6061. Okay, so the shear modulus G is like the elasticity modulus for twisting, for torsion. So let's go to a reference that can help us with that. A lot of manufacturers will post the material specs for the materials that they sell right online. And so here is something from MatWeb from a company ASM for 6061-T6. And if you'll notice, we've got a shear modulus of 26 gigapascals right here. So G equals 26 gigapascals. And then we also need to find the ultimate strength. So here's our ultimate tensile strength of 310 megapascals. So here is our setup. So we wrote down all our givens, what we're trying to find. Based on what we're trying to find, we should use these things. And based on all that, we need to look something up. So next, let's calculate our first problem. We're looking for torque on the shaft. So we're going to rearrange this equation here. We're going to look for torque in Newton meters equals power in kilowatts times 9549, our conversion factor, over N in RPMs. So this becomes just plug and chug. 7 kilowatts times 9549 all over 300 RPM, and that gives us 223 Newton meters. Now this calculation is very important because if you'll notice, we need to use this torque in shear stress and in angle of twist. A lot of students get stuck right here because they don't see the path from what's given, which is the power and the RPMs, to the shear stress. You have to take this step to find the torque first and then use this value here in later calculations. So our next thing to do is find the stress at the ends. Now, to find that stress, we're going to use this. Shear stress equals the torque times C divided by J. Well, we've got torque. We can easily find C. C is half of the diameter where you're interested for a solid shaft here, or a hollow shaft for that matter. It's the distance from the centroid to the outermost fiber. In this case, it's right here for the small end, and right here for the larger end. So it's going to be 25 millimeters here and 20 millimeters here. So that's easy to find C. J is a little more complicated. So let's calculate J for the 50 millimeter end first. J equals pi times d to the fourth all over 32. Pi times 25 millimeters to the fourth all over 32. And that gives us a fairly large number, 614,000 millimeters to the fourth. Okay, now that we've got that, let's plug in. So our shear stress equals TC over J. Torque is 223 Newton meters. Our C is 25 millimeters. And our J is 614,000 millimeters to the fourth. And there we go. So that's where we got all of those from. And that all calculates out to 9.08 megapascals. Okay, let's do the same thing then for the other end, the 40 millimeter end. This is J of 50, this is J of 40, pi times 40 millimeters to the fourth over 32 comes out to be 251,000 millimeters to the fourth. And our shear stress is the shear stress at 50, shear stress at 40 is the same torque. You got the same torque all along the shaft, 223 Newton meters times 20 millimeters is C there, all over 251,000 millimeters to the fourth, and that yields 17.8 megapascals. So notice how we just sized down by 10 millimeters, about 20%, but that yielded almost a doubling in the stress between 50, which is only 9 megapascals, to almost 18 megapascals. So this is the stress at the end. Here's torque on the shaft, stress at the ends. Next stop, stress at the shoulder. Now, this requires a different type of calculation because this is a stress concentrator. If you look at this, as the load is transferred from one end to the other, it has to, if you will, squeeze down, or open up, if you will, but squeeze down from this end to the other. That creates a stress concentration, and that needs to be addressed using some of these charts that we've seen in a previous video. So let's go to that chart that I was just mentioning. This is a chart from an excellent textbook that I've used in the past. This is the appropriate chart. Notice how you have to make sure you get the right one. This is round shaft, that's what we've got. It's solid, that's what we've got. Shoulder fillet, yep. In torsion, because you'll see another one maybe where it's in bending. So this is in bending with a moment rather than in torsion. Very similar looking graphs, but you got to make sure you're doing the right one. Okay, so let's look at what we've got going on here. What we need to do for these types of stress concentration procedures is to calculate a couple of ratios. So here we have D over D, and here we have R over D. These different curves are associated with a different ratio of these parameters. So on ours, we have D over D is 50 millimeters over 40 millimeters yields 1.25. So our curve would be 1.25. So probably close to the 1.20, but doesn't show it exactly. Okay, the R over D here, our R over D is 5 millimeters over 40 millimeters. And coincidentally, it's exactly 1/10 of that, 0.125. So we need to find that location on this axis. So let's do that. 0.1, 0.15, right in the middle. Perfect. So this line represents our R over D that we need. Here's our 1.20 line. So we're looking at something just a little bit above 1.20. The next one's 1.33. So maybe something like this. Okay. And if we follow that over, we get somewhere around here. I'm just going to call it 1.3. This is 1.0, 1.2, 1.4, right in the middle. Call it 1.3. It's hard to get exact and precise on these. Okay, so our KTS is 1.3. Okay, now we can go back to our problem solving sheet. And the way this works is we take the higher nominal stress, in other words, the nominal stress of the smaller portion, the 40 millimeter portion, and we multiply it by that KT to find our maximum shear stress. Called the nominal stress, but the highest nominal stress between these two. So we'd be using the 17.8. 1.3 for our K value times 17.8 megapascals gives us 23.1 megapascals. And that is the stress at the shoulder. All right, so far so good. Before we move on, the units here might be a little confusing. So let's write them down. Newton meter times millimeter all over millimeters to the fourth. Well, we've got newtons, meters, millimeters, and millimeters to the fourth. We should change this to millimeters. 1,000 millimeters per meter. Okay, that will help out. So if you were off by a factor of 1,000, you're wondering why? Probably because of this one right here. Now, our millimeters on top cancel out with millimeters to the fourth here, so we're ending up with millimeters squared. So we end up with 1,000 newtons per square millimeter, and a newton per square millimeter is actually a megapascal. So this is 1,000 megapascals. So whatever number you had in your calculator from 223 times 20 divided by 251,000, you multiply that by 1,000 and then tack on megapascals. So that's how that works. Okay, moving on to the angle of twist. Our formula is the torque times the length divided by the polar moment of inertia multiplied by the shear modulus. Well, we have all of those for the two different sections, the 100 and the 200 millimeter sections. So this should be pretty easy plug and chug, just have to worry about the units coming out right. Now, one more thing we're going to assume is that this section here, that is the shoulder, we're just going to assume that's just part of the 200 millimeter section of the 40 millimeter diameter. We're not going to try to calculate the exact angle of twist for that section. That would take some calculus and would barely affect the results at all. So we will simply assume that it's 40 millimeters all the way through the shoulder, and then it steps up to 50 millimeters. So theta is TL over JG, torque of 223 Newton meters. And let's do the 50 millimeter section first. So our length is 100 millimeters all over J. J we calculated already, 614,000. 614,000 millimeters to the fourth times G down here, 26 gigapascals. All right, gives us 0.0014 watts. Look at this. We've got Newton, meters, millimeters, all over millimeters to the fourth gigapascals. So let's flesh this out. We've got Newton times meters, which is 1,000 millimeters, times millimeters, all over millimeters to the fourth, times a gigapascal, which is 1,000 megapascals. Okay, so now we have everything we need. Oh, that megapascal is a Newton per square millimeter. All right, so let's cancel out everything that we can, and we end up with a Newton on top, Newton on the bottom. I got two sets of millimeters on top, cancel those out with those, and then we've got the millimeters squared now on the bottom, and that cancels out with that. So we end up with unitless. Okay, well, it's an angle, so it's actually radians. Okay, so we end up with all of these units canceling out. We just keep the same value here, which is 0.0014 radians. Then we multiply that times 180 degrees over pi radians, and we end up with 0.08 degrees. Okay, and that's what the angle is going to be just in this section here. This section is going to be going through a twist of 0.08 degrees. So now we need to do this section here. That's 300 minus 100, so the length's going to be 200 millimeters. So theta of 40 equals TL over JG for the 40, and the torque is the same, 223 Newton meters. Length is 200 millimeters, and all that's over. Now it's got a different J that we calculated down here, 251,000. Millimeters to the fourth, and G is the same, 26 gigapascals. And instead of going through all that, I'll let you check my work, and you'll see we come up to a lot larger of a deflection, 0.39 degrees. So what we'll do next is we'll add them up, the twist from this part and the twist from this part. So total and that's pretty easy to do. That's 0.47 degrees, so just about half a degree. So our total angle of twist is 0.47 degrees, and all that's left now is to find this allowable power based on ultimate strength. So let's find our allowable stress. Got allowable stress equals ultimate strength divided by 12, and our ultimate strength, as we looked up over here, is 310 megapascals. Divided by 12 gives us 25.8 megapascals. So that's our allowable stress. So what we do here is we set that allowable stress up as our maximum stress in our other equations. So we're going to use the stress equation for torsion, Tc over J, and this is good for finding our nominal stress. But what we can do is we can set that equal to our maximum stress over 1.3, because we got that from our stress concentration, that 1.3 factor. So we plug this in to tau max over 1.3. So what we do is we rearrange this equation for torque equals tau max over 1.3 times J over C equals 25.8 megapascals times, now remember the J is for the 40 because that's the weaker area, times 251,000 millimeters to the fourth, all over 1.3 times 20 millimeters, and we get our torque of 249,000. Oh my, we've got megapascals, and this is millimeters to the fourth here, and this is millimeters. Oh goodness me. So we've got millimeters to the fourth on top, millimeters on the bottom, and a megapascal is a Newton per square millimeter. So we've got millimeters squared on the bottom, millimeters on the bottom, so it's millimeters cubed on the bottom, canceling out with millimeters to the fourth on the top, so we end up with Newton millimeters, and if you multiply by 1 meter over 1,000 millimeters, you end up with 249 Newton meters. Whew. Okay, so now that we've got the torque, this is our maximum torque, we can plug this back into the very first equation we used right here. We have maximum power equals T in Newton meters times N in RPMs, all over 9549. We plug that in, we get the 249 Newton meters that we just calculated. We get the 249 Newton meters that we just calculated times 300 RPM. Then we divide by the 9549, and we get 7.8. And this, of course, is in kilowatts, as was given over here. So we've finally found our maximum power that we're allowed to transmit based on this design, and it's 7.8 kilowatts. We started with 7 kilowatts, so we're actually pushing kind of the upper bounds here of what we should be doing here. So it's a good design. Nothing we would necessarily have to change on this one. In summary, this was about the torsional stress that comes from power transmission, and this one even had a stress concentration in its design. We discussed first how power can be developed from torque going at a speed in terms of the physics, but we usually use RPM, so we needed to add this factor on. And then as we used other units, we had to add in some other factors in here, and so we have some shortcut formulas here. Then we dove into the problem using this shaft design, and we were given that the material was this aluminum, we were given the power and the speed, and we were told to find these various things all the way to allowable power. So from there, we figured out which equations we needed to use. We used our power equation, stress, angle of twist, and polar moment of inertia, and we had to look up a couple things about the material. Going through our calculations, we used this rearrangement of the power equation to find our required torque, and that's key because that torque is used in stress and the angle of twist, so we needed to use that in several different locations. So from there, we needed to find the stress, but in order to do that, we needed to calculate the polar moment of inertia. We did that we found the stress at one end, the larger end of the shaft. Then we did the same thing to find the stress at the smaller end of the shaft and noted that it was about twice that. Then we discussed the stress concentration at this radius and had to use a chart to calculate the stress concentration factor, KTS. We multiplied it by the stress of the smaller area, which is actually the larger stress, and we came up with a maximum shear stress of 23.1 megapascals. The units figured heavily in here. We had to keep track of everything very well. Otherwise, we would come out with some really high or tiny numbers. Then to calculate the angle of twist, we had to break it down into two sections, the 50 millimeter diameter section and the 40 millimeter diameter section. 50 millimeter diameter section was 100 millimeters long. The 40 was 200 millimeters long. We just plugged those numbers in. We canceled out all sorts of numbers and units, and we ended up with no units whatsoever, which ended up being radians, which is a unitless angle, and we have translated that into degrees. We did that for the 50 and the 40, and then we just added them up to make about half a degree of twist. Then to find the allowable maximum power transmission for this shaft, we used the design factor found in the book and divided the ultimate strength by the factor 12 and came up with 25.8 megapascals. Using that and rearranging some of these equations, we found that our maximum torsion would be 249 newton meters, and then we plugged that back into our power formula, and we ended up with 7.8 kilowatts. This was quite a lot to take in, but I hope that this has helped you understand torsional stress and power transmission, angle of twist, and so on. Also, I hope that the setup here helped you understand how to simply set up problems better, and that organizing everything to begin with can help you figure out how to proceed in a problem and ultimately solve it effectively. Well, I hope this video really helped you, and I encourage you to keep watching videos to improve your knowledge and abilities in strength of materials and mechanics of materials.